Hello everyone. Let us study Module 4 of Aerodynamics 2. Module 1, Module 2 and Module 3 we have studied in class. Module 1 was all about basic equations of compressible flow like continuity equation, momentum equation, energy equation, velocity of sound and their significances and applications and problems. And also we have studied flow through different types of passages like flow through convergent nozzle, flow through divergent nozzle, flow through convergent divergent nozzle, which was all about module 1. And then we have studied module 2, everything about normal shock waves, what happens to the flow properties downstream of the normal shock wave, what are upstream properties and downstream of normal shock wave properties, and then what happens to flow properties, the ratio of flow properties like static pressure ratio P2 by P1 in terms of upstream Mach number M1, rho 2 by rho 1 in terms of upstream Mach number M1, T2 by T1 static temperature, and then stagnation pressure ratios like P02 by P01, and then change in entropy ratio, that is S2 minus S1 in terms of upstream Mach number M1. All those derivations we have seen, and related problems also we have solved. And then module 3, oblique shock waves and expansion waves, where we have seen the difference between normal shock waves and oblique shock waves, and expansion fan, right? And then we have also derived a Prandtl-Meyer relation for oblique shock wave, and what else we have studied in module 3, all the static ratios or stagnation ratios like P2 by P1, P02 by P01, rho 2 by rho 1, T2 by T1 in terms of upstream Mach number M1 for oblique shock wave. This is what we have covered in our classes module 1, module 2 and module 3. And let us start with module 4, which is differential equation of motion for steady compressible flow, under which we'll have all these topics, that is basic potential equation for compressible flow and linearization of the potential equation, which can also be called as small perturbation theory. And then methods for solution, we have pressure coefficients, boundary conditions, Prandtl, Lorentz and Goethert rule, Ackert's rule, and then one common rule for transonic flow, and then lift, drag, pitching moments, and then center of pressure for supersonic profiles. This is what we'll study in our module 4. Fine. So let us start with the very first topic, basic potential equation of compressible flow and linearization of the potential equation, also called as small perturbation theory. This particular topic, two topics it is, continuation of one another. So first we'll derive the basic potential equation for compressible flow and we will linearize it, and that is called as small perturbation theory or linearization of potential equation. So basic potential equation for compressible flow. We know according to potential function and stream function definitions, if you remember from your FM, potential function was denoted as phi and stream function was denoted as xi. Phi was defined as not phi, velocity in any direction, like velocity in x direction is equal to differentiation of potential function in that particular direction x. Velocity in y direction, vy, is the differentiation of potential function with respect to vy. That is what was our potential function definition, right? And basic potential equation for compressible flow, we derive it because it is just the methodology to solve any compressible flow problems, one of the methodologies. Fine. So as part of our derivation, we know according to continuity equation, rho AV is constant. Fine. For constant area duct, let us consider A as a constant, and what will happen, rho into velocity will be constant. So if you differentiate rho into velocity, constant will become 0, and then this is differentiation of rho v is equals to 0. So if you differentiate it in all the directions with respect to x, dou by dou x of rho vx, with respect to y plus, which is dou by dou y of rho vy, if you differentiate in all the direction, then it is the summation of differentiation in all the direction is equals to 0. Fine. Then we have Euler's equation of motion, neglecting the body forces. In Euler's equation of motion, we had rho, velocities and pressure forces P, and then body forces F. So neglecting the body forces F, we have only the other terms like rho term is there, velocity terms are there, and pressure terms are there. So in x direction, minus dou p by dou x can be written as rho into Vx dou Vx by dou x plus Vy dou Vx by dou y plus Vz dou Vx by dou z. So similarly, if you take in y direction, minus dou p by dou v can be written as y everywhere, and dou p by dou z if you take z everywhere. So for solving incompressible flow problems, incompressible flow means rho is constant, so we don't have rho term here. So there will be only 4 unknowns, which is Vx, Vy, Vz and pressure P. Fine. So these 4 equations, equation 1 which is this equation, equation 2 and equation 3 and equation 4. These 4 equations are sufficient for solving the 4 unknowns Vx, Vy, Vz and P respectively, whereas for compressible flow, rho is also unknown. So we need 5 equations for solving the 5 unknowns. So let us consider a 5th equation. So additional 5th equation, let us take it as isentropic process relation, which is P by rho to the power gamma is equals to constant. And let us take this equation as equation 5. And now let us introduce the potential function phi definition. We know according to potential function phi definition, velocity in x direction Vx is equals to differentiation of potential function in x direction dou phi by dou x, which can also be written as phi x. Similarly, Vy is dou phi by dou y, which is equals to phi y. Vz is equals to dou phi by dou z, which is phi z. And equation 1, what was equation 1? This was our equation 1, dou by dou x of rho Vx plus dou by dou y of rho Vy plus dou by dou z of rho Vz is equals to 0. Now we will differentiate this equation once with respect to, once we'll keep rho as constant and we'll differentiate with respect to x, and next we'll keep velocities as constant and we'll differentiate with respect to, we'll differentiate rho term. Fine. Then once if we do the 2 types of differentiation of this particular equation, we'll end up having this equation. This equation, rho into differentiation of velocities plus velocity into differentiation of rho. So let us take this equation as equation 7. Now from isentropic process relation, where rho is the function of pressure P. So differentiation of rho with respect to x can be written as d rho by dou dp into dou p by dou x. Fine. So if you remember this term, d rho by dp into dou p by dou x, dp by d rho is a square from our velocity of sound term. dp by d rho is equals to a square. So d rho by dp will become 1 by a square. Then the second term, which is dou p by dou x, is what we want. Dou p by dou x, if you remember equation 2, what was our equation 2? This one, minus dou p by dou x is equals to rho into Vx dou Vx by dou x plus Vy dou Vx by dou y plus Vz into dou Vx by dou z. This is our equation 2. So this equation 9, which is a square, and equation 2 d minus dou p by dou x, if you put it in equation 8, this is what we will get. Dou rho by dou x is equals to minus 1 by a square into rho into Vx into dou Vx by dou x plus Vy into dou Vx by dou x plus Vz into dou Vx by dou z. And let us take this equation as equation 8. And similarly, we have got dou rho by dou x. Similarly, dou rho by dou y can be written like this, and dou rho by dou z can be written like this. Now this dou rho by dou x, dou rho by dou y and dou rho by dou z, we have to substitute in our differentiated form of our continuity equation. In this equation, equation 7, where we will have rho and differentiation of velocities and velocity in differentiation of rho terms. Here dou rho by dou x, dou rho by dou y, dou rho by dou z, whatever we have in this particular these equations, we have to substitute from those equations. Then we'll end up having this particular equation. From this equation, you have to take rho common, because see, rho is everywhere throughout the equation. Rho into something and then Vx rho by a square into something. So rho is everywhere throughout the equation. Take rho common and equate it to 0. You will be left with only this equation. Where if you take dou Vx by dou x common from all the throughout the equation, then you'll have this particular 1 minus Vx square by a square, and then dou v by dou y if you take common, you'll have 1 minus Vy square by a square, and dou vz by dou z if you take common, 1 minus Vz square by a square you'll have. And then the remaining terms if you take, then it will be minus of Vx Vy by a square and into dou Vx by dou y plus dou Vy by dou x. And similarly, if the remaining terms you have to write down. Next, you have to substitute wherever Vx is there, substitute it with phi x, and differentiation of Vx with respect to x, take it as phi xx. Similarly, wherever Vy will be there, take it as phi y, and wherever Vy will be there, take it as phi y. And if the differentiation of Vx with respect to x is phi xx, Vx with respect to x y is phi xy, Vy with respect to differentiation of Vy with respect to y is phi yy, like that. So this particular equation, substituting in terms of phi, we'll have this particular equation: 1 minus phi x square by a square into phi xx plus 1 minus phi y square by a square into phi yy plus 1 minus phi z square by a square into phi zz. Fine. And then somewhere xy and yx, xz and zx, yz and zy. So next what we'll do, we will have to equate phi xy is equals to phi yx and so on. Here this particular term, phi xy is equals to phi yx, phi xz is equals to phi zx, and then phi yz is equals to phi zy. Then it will become addition, phi 2 into phi xy, 2 into phi xz, 2 into phi yz, and then taking 2 common, here taking 2 common, you will have this particular equation, and this whole equation is called as the basic potential equation for compressible flow. So when you are asked only for basic potential equation derivation, you have to derive the equation till here, and if you are asked to also linearize this particular equation, the next step we have to follow. So the basic potential equation for compressible flow is not a linear one, it is non-linear form of equation. You have to linearize it to linearized form for having the final equation. And in this particular equation, a square is also there, where a is also a variable, and that particular variable can be found out using this relation, which is a by a infinity whole square is equals to 1 minus gamma minus 1 by 2 m infinity square into Vx square plus Vy square plus Vz square by V infinity square minus 1. This is a standard equation or standard relation you are supposed to remember. And the next part of the equation or derivation in itself is linearization of potential equation. Linearization of potential equation. Now the linearization of potential equation. So the basic equation, potential equation derivation we have seen. If you simplify it for any slender bodies or planar bodies like airfoil or wing bodies, then you'll have the linearization of potential equation. So what a planar bodies or slender bodies means, where one dimension is more than the other dimension. Fine. So if you take the slender bodies like airfoil, the one dimension, that is x dimension, the length of the airfoil is usually larger than the width of the airfoil or the height of the airfoil, right? So one dimension, x direction is more than y direction, y dimension. Fine. That type of bodies are called as planar bodies or slender bodies. And also this type of planar bodies or slender bodies will have the disturbance in their flow velocities, and these disturbances or small disturbances are called as perturbations. Perturbation, perturbations. Fine. So hence this linearization of potential equation is also called as small perturbation theory. So see the airfoil, V infinity is the velocity which is coming in x direction, and let us also consider the perturbation velocities Vx, Vy and Vz. and Vx is in x direction and Vy is in y direction and Vz is in z direction. Fine. So assuming the velocity components around the airfoil, Vx, which is the velocity in x direction, we have free stream velocity V infinity and perturbation velocity u. So V infinity plus u. Vy, which is the velocity in y direction, which is not having any free stream velocities. There is only one perturbation velocity v, and v is only perturbation velocity w. So only in x direction you have v infinity, and whereas in y direction, z direction, there is no v infinity, only the perturbation velocities are there. And Vx, Vy, Vz are the main flow velocity components, and u, v and w are the perturbation velocity components. Perturbations are very small compared to the main velocity components, that is u, v and w are very small compared to Vx, Vy and Vz, whereas Vy is just small v only and Vz are just small w only. So this Vx is more compared to the other two terms Vy and Vz is what we mean here. Then u, that is the small perturbation velocity component, u is very less than v infinity. Similarly v is also very less than v infinity, and w is also very less than v infinity. And Vx, so u is very negligible, right? So Vx will become nearly equal to v infinity, and Vy is very less than v infinity, and Vz is very less than v infinity. This is the perturbation relations of perturbation theory's basics. Now considering a flow at a very small angle of attack alpha. Now considering the flow at a very small angle of attack alpha, now v infinity is not in x direction, it is making an angle alpha with x direction, right? Then velocity in x direction Vx is equals to we know v infinity plus u, right? But now velocity in x direction will become v infinity cos alpha and plus u as it is, and Vy is v infinity sin alpha plus v. For very small angle of attack alpha, the above equations will become Vx is equals to v infinity plus u and Vy is equals to small v. And now introducing the perturbation potential phi, small u is dou phi by dou x, v is dou phi by dou y, w is dou phi by dou z, and we also have this relation a by a infinity square is equals to 1 minus gamma minus 1 by 2 into m infinity square into Vx square plus Vy square plus Vz square by V infinity square minus 1. This we had from our earlier derivation, and this equation you are supposed to remember. Take this equation also, and we also have this relation Vx, Vy and Vz. Now Vx, Vy and Vz what we had here, that you have to substitute with V infinity u, small v and w. Then what will happen, Vx will become v infinity plus u the whole square, small v square plus small w square, and everything as it is. And then v infinity plus u whole square as a plus b whole square formula, v infinity square plus u square plus 2v infinity u, and rest as it is, and v infinity square taking as LCM. And now in this equation, neglecting the higher order terms like v square, w square, u square, all those things, as they are very small, then what we'll have only 2 v infinity u divided by v infinity square. V infinity top and v infinity bottom will get cancelled, and 2 and 2 will get cancelled. Then what will happen, a by a infinity square will become only this much. A by a infinity square is equals to 1 minus gamma minus 1 into m infinity square into u by v infinity. But a infinity by a whole square will become inverse of this much. Now using the binomial theorem for the above equation, a by a infinity whole square will become 1 minus x into something whole power minus 1 will be there, means using binomial theorem 1 plus gamma minus 1 into whatever was there plus 0 into m to the power 4 u square by v infinity, it will become plus so on. But now the higher order terms like m for 4 and everything, if you just neglect it to 0, only first and second term, that is 1 plus gamma minus 1 into u by v infinity m infinity square will be left with. And we also have the relation between m and m infinity. The relation between m and m infinity is this much: m is equals to 1 plus u by v infinity into a infinity by a into m infinity, and m square will be square of everything. A by a infinity square we have from this equation, and that you are supposed to substitute, and remaining everything is same. So m square is equals to 1 plus a plus b whole square, that you have to substitute as a plus b whole square formula, 1 plus a square plus b square plus 2ab, and a by a infinity square formula from the above equation, and m infinity square as this, and retaining only the first order terms of u by v infinity, that is wherever u square by v infinity square is there, those things you have to neglect. So the second term in first bracket will go off. So 1 plus 2 u by v infinity and 1 plus gamma minus 1 u by v infinity m infinity square into m infinity square, and then multiplying that particular equation and again neglecting wherever u square and v infinity square terms are there. Then finally you will have this particular equation: m square is equals to 1 plus gamma minus 1 u by v infinity m infinity square plus 2 u by v infinity into m infinity square. So this, let us take, after simplifying the above equation, you will end up having this equation, and let us take this equation as equation A. And we also have basic potential equation from the previous derivation. Let us take that basic potential equation also. Now what we have to do, we have to linearize this particular equation. So linearized potential equation is this much: 1 minus m infinity square into 5xx plus 5y plus 5zz is equals to 0. This is the linearized equation. So let us take this equation as equation C and combine equation A and B. This is equation A and this is equation B. Combine equation A and B and take also C. So first take the C left hand side and take right hand side combined equation of A and B, which is 2 into m infinity square. Just combine that equation and write down 2 into m infinity square 1 minus m infinity square u by v infinity, etc. And then the term 1 m infinity square divided by 1 minus m infinity square into u by v infinity. In right hand side, the first term will go v is very less than 1, like that all the terms will go off. First term will go to 0, second term will go to 0, third term will go to 0. Just take that and you'll have the final equation as 1 minus m infinity square into 5xx plus 5yy plus 5zz is equals to 0, and that particular equation is called the linearized potential equation. And when we are neglecting these terms, why are we neglecting those particular terms? We are making some assumptions, and those assumptions and conclusions are: small perturbation equation holds only good for subsonic and supersonic flows, and it can make only subsonic and supersonic flows linear but not the transonic flow. Transonic flow is always non-linear. And subsonic and supersonic flow do not contain gamma term. Transonic flow term contains gamma, and hence perturbation theory will not be applied for transonic. It can only be applied for supersonic and subsonic. It is valid only for slender bodies and planar bodies like rockets, missiles, airfoils, but not for bluff bodies. And for non-slender bodies, the flow can be calculated using the original non-linear equation of basic potential equation. So this is about derivation of basic potential equation and linearization of basic potential equation. We'll continue the class in next video.